This is a follow-up on my episode about Broadcom NVIDIA competition. I want to mention three presentations in particular that support my arguments for Omnivores. So again, Omnivores is a platform for three-dimensional representation of reality. In fact, it's a physics simulation platform being used for robotic simulation and things along those lines, and hopefully in the future for any kind of physical system that can be iterated in virtu and then taped out and then translated into physical reality. So very similar to chip design. So the three presentations are Geoff Hinton, Xiao, and Ilia Sutskever. Let me start with Geoff Hinton. So again, the links are in the show notes. It doesn't matter where these things were. They were all towards the end of 2024. Check the links in the show notes. Geoff Hinton says that intelligence can be learned. In other words, he says the essence prior to the neural net revolution, the common attitude of the AI community was that the essence of intelligence is reasoning. He says wrong, the essence of intelligence is learning. And I find that an incredibly powerful statement. And I find this very powerful because the same applies to physics. And maybe for some people this might be a little bit too subtle now to go into details, but I think it's really, really important. Because the same way when you were doing handwriting recognition in the 1980s, people thought, okay, we need to have some sort of symbolic logic or something like that to express what we see and teach the machine what it sees. And that it never worked. And it eventually ended up being totally different, which is we learned how to interpret handwriting. Intelligence can be learned. And what applies to handwriting, in my opinion, applies to how a robot moves around in the real world, how materials interact with each other, how heat shields of starships react when they go into the atmosphere. Anything can be simulated in virtu if we have enough data and the right algorithms, enough generalization, and enough time and money to train these things. So I think that's a fundamental belief. And I think Ilia's talk, where he said this is the end of pre-training, and I'm jumping around a little bit. This is three presentations here. One is Hinton, one is Ilia, and one is Xiao. So Ilia's talk at New Rips talks a little bit about the end of pre-training. But there's a very important thing that he said. So he says in this segment that GPT wasn't the first autoregressive neural net. It wasn't the first pre-trained model, but it was the first where we really believed that if we train it with enough data, you will actually get whatever you want. In other words, it's a general model which will generalize over a massive amount of knowledge. And I think that's really what I think Omnivores is trying to achieve with physics, right? It's not the first time we try to simulate physics, but we have companies like ANSYS and so on and so forth. They've been trying to simulate physics for decades, but it's built on symbolic logic or something along those lines. In other words, it's built on physics, it's built on knowledge. And the future of physics simulation is we learn physics. We learn physics from scratch, from data, from observation. Now, how we learn this, how this will be done, what kind of training, what kind of data, what kind of algorithms, that's still in the open. These are all new things that need to be developed. PhDs have to be written, technology has to be developed. It's not even clear that Omnivores will be the platform for that. Maybe NVIDIA will not be the company that succeeds. Maybe somebody else will. But this is the path that this is going. By the way, this is also why Tesla is so valuable, because Tesla is doing the same thing. And they have the advantage of having a real robot, the car, that they can actually use, versus NVIDIA doesn't. So, but that's a whole different conversation. We still think Omnivores is the right platform, and therefore that is the future of NVIDIA. The last presentation I want to talk here about, by the way, okay, let me just put in another tangent here. Dick Sutton, the bitter lesson is really the same thing, right? We have to learn intelligence. Sutton now, he's working on plasticity of learning. So it's not just we learn something, but how do we keep learning? It's all about learning. Now, lastly, I want to mention Ted Xiao from DeepMind. I think I've met him at CBPR. He's one of those rare individuals in the AI community that is very good as an engineer, but also interesting to talk to. And like he talks in his presentation about three fundamental, sort of things that robotics foundation models can be worked on. One is scaling laws, context, and evaluation. Scaling laws, what he means with that is that we really don't understand the scaling laws for robotics yet, right? We don't know, like we have the chinchilla scaling laws for text models. We have a lot of empirical data now where we kind of see, let's say, based on certain loss functions, how more data reduces the loss functions or to use a technical term, lower perplexity. Perplexity is defined as when you give a model data, how surprised is the model with this data, or can it match it into some sort of distribution? Lower perplexity just means the model is better, and with scaling laws, we get lower and lower perplexity. That means the more we train, the more the model knows what to do with new data. But this works really well with text because text is already structured. Text has already predefined structure and meaning, words, letters, all these things over millennia have been developed, first orally and then written. So there's a lot of structure. Some people say that language models are really supervised learning, even though it's unsupervised, but it's already supervised by just putting letters one after the other. That's kind of like a supervised thing where you say, well, you're not going to write the word house any other way than HOUSE. So that's already supervised in that sense. Now let's what Ted's saying is that the scaling laws for robotics have not evolved yet. That's it. So we have a lot of work to do, and that brings us to the second problem, which is what he calls high bandwidth concepts, I think, or something like that. But what he really means is the following: like with large language models, we have a clear interface. We have the internet, we have text, and we can learn from that. With robotics, we have the real world and we have actuators that need to be learned because the language of the real world is actuators, whether it's humans with muscles and muscle tensions and tendons and all that, or robots with actuators, or cars with actuators and brakes and pedals. Whatever it is, the actuators are very different. They act on different physics, but that's what we need to learn. So there's a lot of like bespoke training almost by definition. And I think that's where Omnivores comes in. Now, Ted's not talking about this, but I think this is really the holy grail of Omnivores, is that if we can virtualize all of this and train everything in sim with a standardized model of actuators and then translate it into reality at the tape out, we can get much faster iteration, because everything is always about iteration. And talking about iteration, of course, the fundamental problem iteration is evaluation. If you want to iterate something, you have to know when something is wrong and to improve it. So we need evaluation at scale for robotics, again, one of the other problems. So to summarize, I think these three presentations, Hinton, Sutskever, and Xiao, are supporting my argument for Omnivores and the future of NVIDIA. Thank you.